This is a review of naming and formula writing for both ionic and molecular compounds. This front page here has some important reminders for you. Things like charges add to zero for ionic compounds, which is why sodium chloride is NaCl, but magnesium hydroxide is MgOH2. Remember that you can only use your prefixes with molecular compounds, and you should know those prefixes. Probably the most unusual one on the list is that tetra is for 4. The rest of these prefixes are very familiar from math class, like penta is 5, just like pentagon, hexa is 6, just like hexagon, and so on and so forth. It's also important that you know your polyatomic ions. I've got a nice picture of nitrate there for you. And remember that Roman numerals serve the function of showing the charge on transition metal ions and chemical compounds. Before we start this lesson, you need to have a copy of the periodic table that looks like this. You should have received one from your teacher, and if you didn't, you can print one from Schoology. You're going to need this periodic table and some crayons as we go along. I would recommend a yellow crayon, a blue crayon, and a purple crayon. If you need to, you can pause the video at this point and gather your materials. This is a list of common polyatomic ions. This should be able to be found in your chemistry notes somewhere. We expect that you know all of the polyatomic ions that are above the shaded gray line, as they're the polyatomic ions that are the most common in chemical compounds. The ones below the line are a little less common, but we've provided them in your notes as a reference for you. There's no really quick and easy way to do this. My best recommendation is that you make yourself a deck of note cards with the name on one side and the formula and the charge on the other side of the note card, and just practice until you're familiar with your polyatomic ions. One word of caution as long as we're talking about polyatomic ions. The world of chemistry is greatly dependent upon the last 3 letters of names. It's kind of unfortunate that this is our condition, but we just need to raise awareness that you need to pay attention to the last 3 letters of the names. Notice that the names that end IDE, like nitride, sulfide, and phosphide, are just elements that we've pulled from the periodic table and given them their appropriate charge. The endings ATE and ITE are the endings that are associated with the polyatomic ions. So nitrate and nitrite are nitrogen with some oxygen. Sulfate and sulfite is sulfur with some oxygen. And phosphate and phosphite is phosphorus with some oxygen. It is worth noting that if you've already learned the polyatomic ions that end ATE, the polyatomic ions that end ITE are virtually identical except that they have 1 less oxygen. The next thing we're going to do is do a little bit of coloring on this periodic table that you have. I'm going to use highlighter because it shows up better on the smartboard, but you'll probably want to use crayon just because it'll be a little easier and make your paper a little less soggy. I'm going to recommend a yellow crayon, a blue crayon, and a purple crayon. If you haven't found these already, pause the video and go looking for some crayons. Markers would work as well. We're going to color different sections of this periodic table to represent different things for naming. The first elements we're going to color yellow, and these are metals that don't need a Roman numeral because they have only 1 possible charge. The elements that don't need a Roman numeral, that are metals, are the first and second column of the periodic table. And the reason they don't need Roman numerals is that everything in the first column is +1, everything in the second column is +2. Also, aluminum doesn't need a Roman numeral because aluminum is in the +3 column and aluminum's charge is always +3. There are also 3 transition metals that don't get Roman numerals because they also only have 1 possible charge. They are silver, cadmium, and zinc. The silver ion always carries a charge of +1, cadmium is always +2, and zinc is always also +2. Because they don't have variable charges, they don't need a Roman numeral to tell us a charge. The next group of elements I want you to color are the metals that need a Roman numeral. The metals that need a Roman numeral are our transition metal ions, and they need a Roman numeral because they can have many possible charges. There are a lot of elements in the periodic table that need Roman numerals. We have the transition metals, minus silver, cadmium, and zinc, and the inner transition metals are going to need Roman numerals as well. Feel free to pause the video while you get those colored. The last category of elements we're going to color is the collection of metalloids and nonmetals. The metalloids and nonmetals are everything that we haven't colored yet, and that would include hydrogen, as well as all the elements over here on this side of the periodic table. When these elements form ionic compounds, they represent the anions, the elements that form negative charges. The metalloids and the nonmetals can also get together to form molecular compounds, in which case they don't have charges at all. They just get together in the form of their atoms. Once you're done coloring, your periodic table should look like this. We can now use this colored periodic table to give ourselves a set of rules for naming and formula writing. I've copied our periodic table onto this next slide, and now we're going to lay down some rules. If you have two elements that are colored purple, any two elements that are colored purple get together to form a molecular compound. With molecular compounds, you're going to need to use prefixes for both the naming purposes and also to tell how many of each element if you need to write a chemical formula. If you combine a yellow element with a purple element, you're going to get an ionic compound. In the case of the yellow with purple ionic compounds, you don't need Roman numerals because the yellow elements are all elements that only take on one possible charge. Remember, when you put the chemical formula together, however, you need to make the charges add up to 0. Our next category is a blue element with a purple element. Remember, our blue elements are the elements that can take on multiple charges. Because they can take on multiple charges, when you write the name, you're going to need to include a Roman numeral to tell you the charge. And if you see the name, the Roman numeral in the name is serving the function of telling you the charge on the metal so that you can figure out how to make the charges add up to 0. Our next category is a polyatomic ion with a purple element. The only polyatomic ion that can get together with a purple element is ammonium, NH4 positive, because it's the only positive polyatomic ion. But when ammonium gets together with a nonmetal, it makes an ionic compound, and we again have to follow the rules that the charges are going to add up to 0. You can also have a yellow element get together with a polyatomic ion, and this is fairly common because most of the polyatomic ions have a negative charge, and so they tend to get together with metals. Because the yellow elements only take on one possible charge, you won't need a Roman numeral, but again, you must be aware to make the charges add up to 0. The last possibility is that you have a blue element with a polyatomic ion. This will also make an ionic compound, and because the blue elements have variable charges, we will again need to use the Roman numeral to know the charge on the metal and make sure that the charges add to 0. As you look at this list of possibilities, you'll notice that there really is only one place that we get to use the prefixes. You get to use the prefixes if both of the elements in the chemical formula happen to be either happen to be nonmetals or metalloids, the elements over here in the purple region or hydrogen. Let's try a couple of examples to see how this works. I've again copied our colorful periodic table onto the top of the page so that we have it. In our first example, we have silicon, which is right here, and oxygen, which is right here. That gives us two purple elements, the only situation that we're allowed to use the prefixes. The rules for the prefixes state that you will only use a prefix on the first element if there's more than one of them, but you will always use a prefix on the second element. That means that this compound, SiO3, is silicon dioxide. Our next example combines molybdenum, which is right here, with chloride, which is over here. Because molybdenum is in the blue region of the periodic table, we're going to need a Roman numeral to specify the charge on the molybdenum. To help us out here, we're going to do a fill the box. We know in our chemical formula that we have 1 molybdenum and 3 chlorides. I've put the charge in on the chloride because we already know that charge. It's the -1 right up here. We have to figure out the charge on molybdenum to include that in the name, and we're going to take advantage of the fact that we know this whole mess has to add up to 0. If I have 3 negative charges there, I'm going to need 3 positive charges on my molybdenum, and so my molybdenum is going to be a molybdenum 3. So this compound is called molybdenum 3 chloride. The Roman numeral was needed because the molybdenum is a transition metal with variable charges. My next compound is a polyatomic ion, ammonium, with a purple element. That means I have an ionic compound, and I simply have to name the positive ion, name the negative ion. So this compound is ammonium oxide. It takes 2 ammoniums at -1 each to buddy up with the oxygen at -2. Now we're going to try going the other direction, from name to chemical formula. My first one is cobalt nitride. Here's cobalt. It's in the blue region, and you'll notice that because of that, it got a Roman numeral 2, because we wouldn't have any other way of knowing the charge on the cobalt. And also notice that the word nitride ends IDE, and that means that we need to pull nitrogen from the periodic table and give it the charge indicated by its column. So we're going to be working with an N3-. Again, to help get the chemical formula, we're going to use a fill the box method. Cobalt is +2, indicated by the Roman numeral in its name. Nitrogen is a -3, and that IDE ending tells me to use the negative version rather than the uncharged version. And now I just need to fill the box with enough +2s and -3s to give myself 0 total charge. So I can fill that up with 3 cobalts and 2 nitrogens, and my chemical formula is then CO3N2. Notice that this Roman numeral serves the function of telling me the charge on the cobalts over here. It doesn't tell me how many cobalts are in the chemical formula. And that's one very common misconception. People try to use the Roman numeral to say how many, when in fact the Roman numeral is telling us the charge. One last example brings to light the difference between nitride with an IDE ending and nitrate with an ATE ending. For our last example, we need some strontium, and if we look on our periodic table, strontium is right here. It's in the +2 column, so you'll notice it doesn't have a Roman numeral because it doesn't need one to tell us its charge. Nitrate is one of the most common polyatomic ions, and so we'll use fill the box to figure out our chemical formula. Here's my strontium at +2. Nitrate is NO3 with a -1 charge. To make my box equal 0, I need a second nitrate. So I'm going to use 1 strontium and 2 nitrates. Because I need more than one of this polyatomic ion, I'm going to include a parentheses there to show that I want 2 of these nitrate groups. So I package up the nitrate and put a 2 right there to get 2 of those groups. So hopefully this gives you a second look at how to name chemical compounds, just in terms of thinking about what types of elements are involved, what type of compound is created, and do I need a Roman numeral or not in order to name that particular compound.